Hello everyone, my name is Oleg Gleiser. I'm the director of UCLA Math Circle. We are here at the Math department in our beautiful lecture room MS 5200, and I'm about to give a lecture to Parents Club at our Math Circle. Basically, when kids are taking math classes, we try to entertain parents by occasionally giving them popular science lectures. And this one that I'm about to give is called Introduction to Game Theory through the Game of Chicken. So again, thank you so much for coming. This is a Parents Club for UCLA Math Circle. We are extremely grateful for bringing your kids here to learn math with us. We are extremely grateful for your support, especially these troubling times. We expect to have more of your support if you can afford it. But now let me present the topic, Introduction to Game Theory by means of the game of chicken. And the way you play this game, and you probably, most of you, at least anyone who drives in Los Angeles and vicinity knows this game from practice. Probably not the name, but the essence of the game. So imagine player one drives their car down the street. And at the same time, player two drives their car down this perpendicular street. And the cars are more or less of the same type, let's say two family sedans. The game would be different if one of them drives an 18-wheeler and the other a motorcycle. But it's two probably equally sized cars, and there is no traffic light. And it's mostly gents playing this game. I haven't seen ladies engaging in such type of behavior, but you know, I did it a couple of times, I have to confess. So you want to pass first, right? You are busy and you are more important, and, or maybe you are not in the mood, or whatever your reason is. So you have two strategies. One is to drive through. So player one is here, player two is here, and I'll make a table of expected payoffs in a moment. So I have two strategies, to drive through and, to chicken out, to swerve at the last moment. Unfortunately, player two has the same payoff strategies available to them, drive through or chicken out. And depending on our choice of strategies, we get some expected payoffs. So if we both, tough guys, we decide to drive through no matter what, it's a negative large number for each of us. The cars are totaled, we have health issues, so on and so forth. And L stands for a large positive number, so negative L is very, very bad outcome. So if I decide to drive through and this person at the last moment chickens out, you know, I get a boost to my pride. You know, I get one util of pleasure. Now, pleasure is not really measurable, but here we are actually indicating our preferences, and the numbers don't really matter as long as we know that this is a huge negative number and this is a relatively small positive number compared to that huge one. And well, that poor thing, they get their ego hurt and they get negative one util. And of course, it's the other way around. If it's the other way around, they drive through and I chicken out, I get negative one, they get positive one. And if we both chicken out, then no bad or good emotions, no physical damage, 0 and 0. So this is a famous game theoretical model known as the game of chicken. So it seems to be extremely simple, but let's solve it first. And what does it mean to solve a game? It means to find Nash equilibria. So most of you, probably all of you, have heard the word, but just in case, let me give you a precise definition. A Nash equilibrium, or NE. What is it? It's a pair of strategies. So strategy one for a first player and strategy two for a second player, such that, so let me first tell you and then I'll put it in writing. No player has an incentive to unilaterally switch to a different strategy. No incentive meaning if they switch and the other player doesn't, the switching player either would get the same number of utils or less. And switching takes some effort, so they lose anyways. So let me put it in writing. A Nash equilibrium is a pair of strategies such that either player has no incentive to switch unilaterally. Okay, so this is a Nash equilibrium. And what I'm going to do for you, I'm going to show you how to find pure Nash equilibria. This requires pretty much no math. So the way you look for pure, and everything I'm saying generalizes to more than one player. More than two players, my apologies, to 3, 4, 5, whatever, any finite number of players. I'm not going to do it because I want to keep this talk at the popular science level. And for 3 players, you will need a 3-dimensional box of numbers, 2 by 2 by 2 matrix, which is called the tensor. And I don't want to get into that. It's not complicated, but just introducing all this stuff will take too much time. So I'm thinking, if they choose to drive through, what is my better response? Well, if I choose to drive through as well, it's negative L. If I choose to chicken out, this is obviously better for me. So I mark it with a star. And if they choose to chicken out, what is a better outcome for me? Well, 1 is better than 0. So I mark this 1 with a star. And the other player, they do the same computation. They think, what if Oleg drives through? Well, I better be here than here. And what if I know Oleg is a chicken, he will chicken out. Where am I better off? 1 is better than 0. And we get to what's called pure Nash equilibria. So P and E, pure Nash equilibria. And these are drive chicken and chicken drive. And the payoff in this case is 1, negative 1. And the payoffs in this case are negative 1 and 1. So extremely elementary. I wouldn't even call it math. It's just common sense, right? And you look at this game, and it doesn't yet explain anything with regard to tariffs or kids fighting or anything complicated, because the most interesting one is a mixed equilibrium, and so far it's hidden. But I think in terms of pedagogy, when I talk about middle school, I'm absolutely serious. One day we're going to have it. I'm working very hard to have a brick and mortar school in Westwood. I'm not going to be the head of school. I want to be on the board, but I want to find the money and hire a team. We will be teaching thinking kids from middle school on thinking ahead of time and figuring out pure Nash equilibria and then rationalizing their behavior based on that before they act. And I'll show you a really cool example about kids choosing whether to engage in a fight a little bit later. But for now, there is one crucial piece of theory needed. And it seems to be that many people who have heard of Nash equilibria, most people actually don't know about it. Because normally things are more complicated than either or. It's a mix of both, right? So what is a mixed Nash equilibrium? I start thinking, how can I make my opponent, the person I'm playing against, to be indifferent about choosing either this strategy or that strategy? Well, let me put two probabilities here, P and 1 minus P. Since there are only two strategies, right? These two numbers, and P is in between 0 and 1. So it's a probabilistic weight. And of course, if there are 5 strategies, then the sums of those weights must always add up to 1, so you get 5 fractions. In this case, you only get 2 because these 2 fractions, they add up to 1 to the entire, probability that something happens, anything happens. So, and how can I think about it? There are 2 ways. If I play this game many times over and over again, and that's what the federal government is doing with tariffs, these are just frequencies. I heighten my tariffs on trade with China to 2,000%. Oh, next day, actually, no, 2,000, I didn't think much, oh, it's 20. Oh, no, it's actually 1,000. Oh, no, it's 10. So back and forth, back and forth. And you can think about it some ridiculous percentage here is driving through and wrecking both economies. Some very low percentage is chickening out, and you can count the frequencies and actually put the actual numbers here. Or alternatively, when it comes to a game that can be played only once, if it's really me and my opponent is driving through or chickening out, I can, knowing the math behind this game, I can think about it this way. What if I have a random number generator in the following sense? I have a coin, probably programmed in a computer, such that heads appear with probability p and tails appear with the complementary probability 1 minus p. So I toss this coin in my head, and depending on what side I get, I either drive through or chicken out. And then my expected gain is a mixture of the two with such weights. So let's see what that is. But for now, I'm looking for a mixed Nash equilibrium, so I'm thinking, can I find such a probability p of myself driving through which equalizes the gains of my opponent with regard to their strategies chosen? So let's see. If they choose to drive through, and it's a function of p, right? So their gain is negative L, but taken with this weight. Negative L times p plus this gain taken with that weight plus 1 times 1 minus p, and that equals, and you see this is really elementary school math. The concepts are extremely deep actually, so I won't teach this to elementary schoolers, but the math itself, I mean, even I can do it without making a mistake probably, right? Negative LP plus 1 minus p. I'll keep it this way. I'm too lazy to simplify this formula. And what would be the gain of my opponent if they choose a different strategy, and the only one different strategy available is to chicken out? So if they choose it, then in this case their payoff is negative 1 times that weight p, and in this case their payoff is 0. Let's still spell it out, 0 times 1 minus p, and what is it? It's negative p. So if I choose p so that these two payoffs are equal, then my opponent will, whatever strategy they will have no incentive to switch, right? And the game is symmetric, so whatever computation I do for my opponent in my head, they do the same for me in their head. So neither of us has an incentive to switch. What is it? It's a Nash equilibrium, this time a mixed one. So let's solve the equation. Negative p is equal to negative L times p plus 1 minus p. Negative p and negative p conveniently cancels out, and we have 0 equals to 1 minus L times p, or L times p equals to 1, or p equals to 1 over L. And it's not 0. It's a small positive number, but it's not 0. And of course, the complementary number 1 minus p is equal to 1 minus 1 over L, which is equal to L minus 1 over L. This number is almost 1, but not quite. So there is a third Nash equilibrium over here, right? And that is 1 over L and L minus 1 over L for the first player, and the same 1 over L, and it's actually a vector, so let me write it down as a vector, kind of 1 over L and L minus 1 over L for the first person, and the same for the second person. Here is one more Nash equilibrium, and what are the expected payoffs? They're symmetric, of course, so it's negative p. So the expected payoff is negative 1 over L and negative 1 over L. Now let us compare this pair of numbers to these two pairs of numbers. And what you see, if you play this game this way, you lose, but you lose very little. As opposed to here, you know, either you lose a lot or you risk your life. So what type of behavior is rational in this case? The only one, right? So I looked at it, and actually, is Alan here? Yeah, I have one student here in the room who was present when I was teaching this course, and I'm looking at it, I'm like, the tariffs, no tariffs, you know, he's going to be doing this thing just to show that they can act crazy if you talk about the federal government. But in the end, the market will lose very little in value and come back. But all I'm saying is, this explains what happens in this tariff war with equally strong partners like European Union, like China, unlike, unfortunately, Mexico and Canada. Although our largest trading partner in volume is Mexico and number 2 is Canada, they are not, they will be hurt way more than us. So if you recall this picture, I said at the very beginning, it should be 2 equally sized cars. If one is an 18-wheeler and another is a motorbike, you know, it's a different game. We can play it too, but it's a different game. So, and that's exactly what happens, right? You see, the point of game theory, you don't even need the math. If you have this background, you look and you know. So it's really eye-opening. So European Union already settled. China, there is no way either for the US or for China to decouple. So they're going to be wrangling around for a while, but in the end they will settle for a treaty, and the market will shrink a little bit for some period of time, but there will be no big damage. Any questions? All right. So now I hope you start thinking that game theory is something you want to know and you want your children to know well before they actually go to college, because one of the games that my students kind of offered me to investigate is this: to clean or not to clean. Meaning, you get in a dorm, you have a roommate, and you have different levels of cleanness, right? So what are the strategies available to you? Don't clean at all. Clean only your area, clean everything. What are their strategies? The same. And you can ask and figure out. You cannot write down the exact number of utils, but you can figure out the preferences. Solve the game. Most likely it will be a mixed Nash equilibrium, which will make life easier for both of you and have a happy life in the dorm. All right. So before I switch to another example, let me slightly generalize. What I just showed you is a two-person zero-sum game in the strategic form. You know, scientists, they like those complicated words because, you know, I have to show to everyone that I'm a learned person. You know, I know some complicated words, although sometimes I don't quite remember how to spell them, right? So a two-person non-zero sum. Sorry. Did I say zero sum? Oh, no. General sum game. Yeah. General sum game in a strategic form. So we just saw an example. Let me generalize, give you the definition, and leave it at that. So you have two players. And as I've said, you can generalize to more than two players, but then you have to deal with tables of numbers that are 3, 4, 5, 66 dimensional, and we don't want to do that. So player 1 is traditionally here, player 2 is traditionally here. Player 1 has a set of POS strategies. Let's call them S1, and there are S11, S12, S1M. M POS strategies, and let me mark them here. S11 is here, some random strategy S1I is here, and S1M is down here, and they create rows of this payoff by matrix. And the second player, they have their own set of POS strategies, which are S21, S22, so on and so forth, S2N. In general, the game is not symmetric, and the number of POS strategies available to each player is different. So here we have it, S21, so on and so forth, some random strategy S2J, S2N, columns. And they give us columns of the matrices. There are two matrices, and here at the intersection of the i's and j's column, we have payoffs, Aij for the first player and Bij for the second. So this is called the bimatrix of payoffs, and that's all you need to know about this game. Once you move to more players, finding pure Nash equilibria becomes more complicated, but not super complicated. So that's the entire theory of two-person zero-sum games in the strategic form, probably. In the strategic form, because we list the strategies and we list the payoffs, and that's what it is. And another amazing feature of those games is there are like really a small number of games. The famous Prisoner's Dilemma, the game of chicken, and then a few more. And they really describe pretty much any, and of course this is a very simplified model, bare bones, but they describe any interaction with a human or business interaction or social interaction or political interaction between countries, blocks of countries and whatnot, and you'll see in this lecture. So they're very simple and they're very eye-opening, as I hope you agree with me by now. Any questions? All right. If you don't have questions, I'll not generalize too much. General theory is usually boring unless you mean to apply it pretty soon to some interesting particular example. So let's see. Let me erase all this and let me kind of look back at my childhood. I went to school and occasionally I picked up fights and my mom was not happy and my teachers were not happy, and sometimes when I lost those fights I was not happy. And sometimes when I won those fights and all these troubles started happening, I was even less happy. So, and I promised to show you that the same game of chicken describes the situation which almost every boy finds themselves in during their middle school age, right? So what are the possibilities? So I just showed you what a game in the strategic form is. So now I'm going to show you games in, I keep forgetting this word, so I'll look it up. Extensive form. Games in extensive form. Yeah, let me just make a quick sip of coffee. So here we are. It's me and another boy in this room. And what I'm going to draw now, I'm going to draw a tree of a game. And given, and a game described by its tree of decisions, the tree of choices, if you may, that is called a game in extensive form. And to solve the game, you have to rewrite it in the strategic form and then apply the same math. But sometimes just writing down the game solves it because, as you'll see in this case, interactions are pretty straightforward. So it's me and another boy that doesn't like me, and we are both in 6th grade, and we meet in the canteen and we look at each other. And two things can happen. Either we ignore each other and it's a separate graph, it's just 1 point. So we are like, it's not worth it, right? Nothing happens. Or I decide to choose, you know, I can ignore his looks. And then I lose a util because, you know, I just chickened out. And there was the girl looking at me and she saw me chickening out, so I'm like, And he's like, yeah, you know, he's a proud boy, right? I chickened out. Or I can pick a fight. And if I pick a fight, the sad thing is, if I win, my mom will make it hard for me. If I lose, also pretty bad. And again, you can play with the number of utils and make a model slightly more complicated. And you can make this tree of choices more complicated depending on, you know, if you are a psychologist studying child psychology, you can make this tree quite complicated and do a lot of computations and figure out many more things. But I prefer to stick to this level to demonstrate that the game of chicken is the same model behind what kids do. And again, I'm not looking at some really rare cases when, you know, it's like a 10th grader beating up a 1st grader. That's sick. I'm looking at like two equally sized family sedans, two equally sized 6th graders, you know, deciding whether to slug it out or not. So what do we have here? To solve this game, and you already start seeing that it resembles the game of chicken. It's two graphs, actually. This graph, it has two connected components because this vertex is not even connected to this graph. So I start rewriting it in the strategic form. So what strategies are available to me? Fight or ignore? right? And the same for my opponent, fight and ignore. And what are the payoffs? If you both fight, it's negative L, negative L. If I choose to fight and he chickens out, it's what? I'm proud of myself, and the other way around. And if you both ignore each other, it's 0-0. It's the same game of chicken. And the large language model that we call our intuition, it works exactly the same way, I'm pretty sure, for humans as it works for computers. We have enough experience. So without knowing anything about the game of chicken and its mixed equilibrium, every boy knows that it's better to not to pick up a fight, but not always. Once in a while, you have to show that you're crazy and you can do it. Right? So I'm not going to even write down the numbers. You see, it really catches up that behavior. Or recall any Hollywood movie about school bullying. I mean, they're all terrible, poorly made, and like low budget and all this. But the point is, what do we see? What is a good behavior expected by the viewers? You know, this kid, he's kicked around, and he doesn't pick up a fight, and he doesn't pick up a fight, and then all of a sudden he's Captain America and just like, you know, destroys the whole neighborhood, right? but the thing that is behind it, probably without those people who write scenarios for those movies, is that we subconsciously know this answer, and we perceive this type of behavior as kind of good, advantageous, whatever, you put a label on it. So that's about kids fighting. How is this related to politics? Okay, let me start with the Cold War. Most of you are probably old enough to remember that this thing was in place between the Eastern Bloc, including the Soviet Union, including Russia, where I'm from originally, and the West. And there was this very simple game, also having the game of chicken behind it. The game in the extensive form, it was called MAD, Mutually Assured Destruction. And the game was like this. The game, it was the Eastern Bloc supposedly starting the game because why? So let me take a sip of coffee, and actually it's a non-mathematical game theoretical observation that again is so obvious that many people kind of miss it. So what makes a country or a block of countries aggressive with respect to another country or another block of countries? Well, we all live in the world of limited resources, so like it or hate it, they compete. They compete for influence, for power, for money, for natural resources, whatnot. And the form of government, again, like it or hate it, it's a machine that runs the society, and not all the machines are equal, or, sorry, I probably have to use this new days language, equitable, right? They don't deliver equal outcomes. Some engines are more efficient, have more power, more, you know, whatever, just more efficient than others. So some countries in the economic area outperform other countries. And back in the Soviet days, Soviet Union was greatly inefficient as any social justice society by design, right? Because how can you be efficient if you have to make outcomes equal for everyone, right? So there should be government officials all the time deciding who gets what, and the whole machine works barely. And because of that, they had to be aggressive. And again, you can extend it to modern days. I don't want to, because I want to keep this lecture completely apolitical. You make your own decisions, but I think that really explains why some countries are more aggressive than others. And actually, communists back in my day, communists on UCLA campus nowadays, they call the US being more efficient, they call it American imperialism. And they hate it, and the reason is, indeed, if this country is more efficient, it's more prosperous, and there are more jobs, and there are more opportunities, especially for people with energy and brains, and they flock over and make this country even more prosperous. And in other countries, they get further and further behind, and they feel offended, and they hate American imperialism, this mysterious force that kind of sucks energy and wealth out of them as they perceive it, right? So again, it's not political, it's their perception. Feel free to agree or disagree, but that's what it is. And that is why the Eastern Bloc is way less efficient than the Western Bloc. They had to be aggressive because, you know, if we cannot get up to their level, we have to pull them down to our level, right? Pretty obvious. So they could choose to maintain peace and then it's 0-0. Or they could choose to escalate the situation from the Cold War to what? And what does it mean to escalate? The idea that was floating in the Soviet military for many decades, and I had the misfortune to serve in there, so they drafted me, so I kind of know because we trained for it a little bit. It was, what if we explode a tactical nuke, let's say, over the US carrier group? They wouldn't be crazy enough to start a global nuclear war, right? But we will put them down and show them that, you know, those capitalist weaklings, you know, they can't respond to us. They're so afraid. And they seriously considered this idea. And similarly for land forces, what if we explode a nuke currently, let's say, over a base in Poland where NATO unloads their gear for Ukraine? They wouldn't start a full-scale nuclear war because of that, would they, right? So it's pretty contemporary. And but getting back to the Soviet times, so the Western Bloc had to decide what to do. They could pull back. And it's like, oh, you know, we have many carriers, what can we do, right? So so Russia is player one, so Russia gains one util, the West, or the Eastern Bloc gains one util, the Western Bloc loses one util, but roughly speaking, no big deal. Or they can retaliate. And this means a full-scale nuclear war, in which case it's negative L for both players. And you have seen this before, right? So what is the difference between this and the game of chicken? I actually talked to some Soviet generals and American generals from that era, and they all agreed that the West, through all the channels possible, communicated to the Eastern Bloc via actually here. If there is one single nuclear explosion over anything you want, we are going to all in. And because of that, of course, the Cold War never became hot. And finally, the last thing, what's going on in Ukraine. And again, I'm absolutely apolitical. I'm not going to tell you my opinion or the side I'm on or whatever. It's just math. And you see, in the last two cases, I mean, I can rewrite this game in the extensive form, in the strategic form, and compute Nash equilibria. But it's the good old game of chicken each time, every time, so we know the answer, except for one thing. In this case, in this mad case, they eliminated the part of the game. They eliminated the part of the tree of the game. They said, no, 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 no. We are not going to pull back. We are going all in. Therefore, this equilibrium is this equilibrium is non-existent. You have to choose between this and this. Ukraine is very different for a variety of reasons, and again, it's not a political science lecture. It's a math lecture. I'm not going to discuss why. I have my ideas, but they're not important, and they may be wrong, actually. And again, unfortunately, like it or hate it, in this case, it's the Western Bloc starting the game because Russia is already in and they cannot pull out unilaterally. Unfortunately, any fight, whether it's a war between nations or a fist fight between sixth graders, there is a Nash equilibrium. Once you are in a fight, you cannot stop fighting unilaterally, right? So imagine Ivan and myself, we get into a fist fight and we are throwing punches, and then I decide enough is enough, and I just stand like this. Right? So we ain't gonna do that. So here, okay, Russia invades, and now the West starts this game, and they have three strategies. They can undersupply Ukraine and let Russia win. So again, unfortunately, I'm not talking about Ukrainians and their utils and their losses. It's a mathematical model. It's the West playing against Russia. And again, it's super simplified because under the previous federal government, the West was united. Now it's not clear whether we are a part of that collective West in terms of supporting Ukraine. Also, Russia currently is Putin, but I have absolutely zero information about his inner circle. They may have different interests, they may have the same interests. So it's a very bare bones model. All right, so the West is player one here. And if we don't give Ukraine enough weapons, they're going to lose this war, and we're going to lose one util, and Russia will gain one util. We'll be like, what can we do, right? We are busy with our own problems. Or we can supply Ukraine to win. This is not going to happen, but it's not actually super hard. Russia doesn't seem to have a powerful conventional army, as shown by Ukrainians. So if we give them enough weapons, they can be in Moscow maybe in half a year from now. However, this trick kicks in, right? Because what can Russia do? Russia can lose the war, or Russia can escalate. And then if Russia escalates, the West can pull back, or they can retaliate. So let's see what the payoffs are. So if Russia loses the war, the West wins one util. Yeah, we help Ukrainians to do that. But unfortunately, Putin was watching the news, and he knows how presidents of Libya, Iraq, and other free countries ended up when they lost their wars, right? So for him personally, it's negative L. So, and he has access to that red button. So, but retaliate if the West pulls back, we get back to this situation, because basically we allow them to conquer Ukraine. So why even going here and having one nuke over that base in Poland if we can undersupply right away? Or we can retaliate, and it's a global nuclear war. And again, the situation is probably different from that with the Soviet Union, because that war would have had no winners. This war, military on every side knows the West can win, but at the cost of like really hundreds of millions of people dead. So it's not really a viable scenario. We don't want to go this way. And there is one more strategy: supply to a standstill. And then there are no winners, there are no losers. And I remember, actually, it's kind of funny. First time I taught game theory here at UCLA, it was 2014, and Russia just annexed the Crimea, and I decided, like, what if I make a game that describes what's going on? And I came up with this tree, and it's so obvious that, I mean, I can make a game in the strategic form and find all the Nash equilibria, and you will see that the only one rational for the West is this one. But it's pretty clear without any computations. So what does that mean? And I told my wife, look, they're gonna freeze the front line eventually, here or there. It doesn't matter for the West where the front line freezes, as long as it's frozen, as long as both sides have exhausted their resources, they have no more willingness to fight. And she was like, Oleg, it's too complicated, and she was very emotional. And I'm like, look, emotions or no emotions, this is the only Nash equilibrium rational for the West. So that's exactly what's happening over there. And you can see that, of course, different administrations of this country, they have slightly different approaches. But it really doesn't matter whether the front line freezes here, 100 kilometers left or 100 kilometers right on the map, as long as it freezes. And then, of course, each side declares themselves a winner, right? And Russia says, look, we have the Crimea and the land bridge, we have won, we have destroyed this terrible place called, Eastern Ukraine or whatever. And Ukrainians say, hey, look, we won, yeah, we lost some territory, but it's temporary and we'll get it back sometime later. But now we are independent and we have our own government, and each side declares themselves a winner, and that's it for this period of time. I actually told my wife back in 2014, look, this is the only thing that can possibly happen. And that's exactly the only thing that is happening. And the rest, unfortunately, is emotions that just kind of muddy the water and make the picture less clear. And again, behind this part of the game, there is the very same game of chicken. But it's not played as not to give even a small chance for the other side to go mad and drive through with nukes.